Good evening, everybody. I am Vibhu Swain from PowerTech Consultant. Today, we shall start our webinar number 36. Let me share my screen with you. So, in this webinar number 36, we shall discuss about the furnace. Particularly, this is for book 4 and chapter 2 of book 4, that is energy performance assessment of furnace under energy efficiency in thermal utilities. Particularly, this is for book 4 and chapter 2. So, those who are appearing for energy auditor examinations or chapter 4, it will be useful for them. Now, we have already discussed in book 2 what is furnace and what are the types of furnace and how furnace is a major energy consuming devices, and what is the benefit of saving energy as far as furnace is concerned. So, to capture whatever we have studied in book 2, let us briefly discuss particularly the industrial heating furnace are devices which is which are used for heating the material, and therefore they are the user of energy, and there are various types of furnace are available. Already we have discussed, like batch type furnace. Batch type means they usually do the job at stationary positions, and there are some type of continuous type of furnace, those who handles large of amount of work at regular intervals. Then few examples of batch furnace are box type furnace, bogie type furnace, cover type of furnace. These are also for mass productions, but for mass productions, continuous furnace are more frequently or generally used. So we have studied about continuous furnace like pusher type of furnace, working hearth type furnace, rotary hearth, working wing type furnace. So these are the major four furnace which comes under continuous furnace: pusher type, working hearth type, rotary hearth, and working wing type furnace. Now, what are the major energy or primary energy used in furnace? There are furnace oil, LHSS, LDO. Also, some kind of secondary energy is used in terms of electricity in the furnace. So, this is an example of pusher type 3-zone reheating furnace. This is an example of working wing reheating furnace. We have already discussed that there is certain charging table which gives feed the material into the furnace. There are burners. There is a soaking zone in which the heat is soaked and the material is taken out, and is at the heating zone. And this is the effective furnace length. Similarly, the burner positions are tilted towards downward, and it does not tilted upward. It should not heat the material. It should not also hit the wall or the ceiling. So these are the type of furnace, and let us discuss now what is the purpose of performance test. Why you require to conduct any performance test in furnace? Because, as you know, furnace is a major energy guzzler, so we need to reduce the energy consumption. Therefore, we need to make a heat balance diagram of the furnace, and we have to also find out what is the efficiency of furnace, what is the specific energy consumption of a furnace. So for these parameters, we need to conduct the furnace performance test. Now, particularly, many factors affect the furnace efficiencies, like capacity utilization, excess air ratio, final heating temperature. So performance assessment, by conducting performance assessment during audit, what we can find out what is the level of efficiency or what is the heat balance of the operating conditions. Then we can compare the same with the design parameters or design efficiency or design heat balance. Then based on the gaps, based comparing the deviation, we can conduct a gap analysis. So we call it gap analysis, and gap analysis is a very good tool as far as furnace efficiency improvement program is concerned. Now, normally in this method, we have followed Japanese industrial standard JIS G0702 method of heat balance for continuous furnace for steels. So this is the method, Japanese method we have utilized. What has happened, in fact, in Japan, JICA was the key partner of Bureau of Energy Efficiency in the past. So they are very advanced as far as energy conservation and energy efficiency is concerned. Now, in certain books, you will find some of the parameters are not considered or ignored. That is also okay. But in this method, we have followed Japanese industrial standard. So you have already understood furnace efficiency is heat output by heat input. That means how much of heat is being carried with the stock. Stock means the materials. Now, how much of heat is being input heat is given to the furnace. So heat carried out in the stock divided by heat input to the in terms of fuel or electricity. So based on by comparing output by input heat, we can find out efficiency. Similarly, specific energy consumption is quantity of fuel or energy consumed per quantity of material processed. So what is the ton of billet produced, or that will be divided with the total quantity of fuel or energy consumed. Through that, we can know ACC, specific energy consumption. Now, as you know, in boiler, there are two methods, direct method, indirect method. Similarly, in furnace also, there are direct method testing, in which we simply divided the heat in stock divided by heat in fuel consumed. That is, what is the heat in stock? That is M. M is mass. Cp is the specific heat. T2 minus T1. T2 was the final temperature desired. T1 is the initial temperature of the billet or the material before entering to the furnace. So from this Q is equal to M Cp T2 minus T1, we can find out what is the heat in the stock. Now, for this furnace heat balance method, and how we can calculate the heat in fuel consumed, we can multiply gross calorific value into the fuel quantity, and we can find out what is the heat input to the furnace. By dividing these two, we can find out thermal efficiency as far as direct method of testing is concerned. Now, in case of indirect method, we conduct a furnace heat balance method. So, what we do, and we tabulate what is the input heat and what is the output heat. Now, in terms of output heat, one heat is supplied along or taken away along with the materials. So that is basically the output heat. But there are certain heat which is lost to the atmosphere in terms of heat losses. So what are those heat losses? Heat loss through exhaust gas, either as sensible heat or latent heat or as incomplete combustion. So there must be some exhaust gas or dry flue gas loss. There will be some heat loss through furnace wall or hearth, and there may be some heat loss to the surrounding by radiation, convection from the outer surface of the wall, and through the opening, through the cracks, through the doors, there will be also some heat will be lost. So these are the heat loss plus some useful heat is taken away by the material itself. So we can conduct a heat balance method for a furnace. Now, for conducting assessment of the furnace, what parameter we need to understood or we need to measure during audit is weight of the stack or number of billet heated, temperature of the stock, temperature of the furnace wall. We have to measure its furnace wall temperature, roof temperature, bottom temperature, area of the furnace wall and roof and bottom we need to calculate. Flue gas temperature can be calculated. Flue gas analysis, we need the analysis, particularly CO, CO2, O2, and we also have to find out what is the fuel consumption through accelerometers. So you have to use different type of instrument like infrared thermometer, fuel consumption monitor, surface thermocle, and other measuring devices. And for specific heat and humidity or temperature, atmosphere temperature, we can use an hygrometer also. Now, with this measurement, we can conduct the furnace assessment studies. Now, let us study an example. because this example is very important, and let us study bit by bit. And this is an open book, so once you understood or once you understand the principle, it will be very easy to calculate these problems in paper 4, which is basically an open book. Now here the given data are oil fat reheating furnace. Operating temperature of the furnace is 1340 degrees Celsius. Now average fuel consumption is given 4000 liter per hour. 4000 liter per hour. Now what is the density? Density specific gravity of the oil is 0.92. From 0.92, what is the average fuel consumption? You know, liter per hour. If I multiply specific gravity, I'll get liter will be converted to kg. So it will be 368 kg per hour. That is the average fuel consumption. Now, what is the flue gas exit temperature after air filter? So there is a certain air filter is there. Flue gas exit temperature is 655 degrees Celsius. Now, what is the ambient temperature? 40 degrees Celsius. And air is preheated, that is the combustion is heated, combustion air is heated from 40 degrees Celsius to 190 degrees Celsius because of the air preheater. Now, what is the thickness of the wall? 460 mm, that is 0.46 meter. Now, what is the furnace billet extraction outlet? That means furnace opening is 1 meter high, 1 meter wide. That means this is a square type of furnace opening, and the area is 1 meter square. So you have to draw a heat balance diagram, identify the heat loss, efficiency, and specific fuel consumption. So what are the other data? 655. It is given flue gas exit temperature, ambient is 40 degrees Celsius, air absolute humidity, it is 0.0437 kg per kg of dry air. Preheated is 190 degrees Celsius. From this we can calculate 368 kg per hour, that is average fuel consumption. O2 is 12%, CO2 is 6.5%, CO is 50 ppm. Weight of the stock is 6000 kg per hour. If I convert it to ton, it will be 6 ton per hour. What is the specificity? It is 0.12 kilocalorie per kg per degree Celsius. Surface temperature of the ceiling. We need this data to calculate surface temperature loss or radiation loss. Similarly, side wall is 100 degrees Celsius, bottom wall or flue duct is 64 degrees Celsius. Area of the ceiling is 15 meter square, side wall is 36 meter square. Area of flue duct is 10.3 meter square. Diameter of flue duct is basically through which the flue duct is exits, and air filter it get into contact with the air filter also 0.4 meter. Then this is the fuel analysis report. Carbon is 85.9%, hydrogen 12%, oxygen 0.7, nitrogen 0.5%, sulfur 0.5. Hydrogen is the fuel moisture in the fuel, that is 0.35%, ash is 0.05%, very little ash because it is oil. So GCV is 10,000 kilocalorie per kg. With this we will try to find out the heat balance. So this is the typical example of the furnace. Stock is going inside, this is the furnace, and this is the air preheater. Now air is coming at 40 degrees Celsius. This is the absolute or the humidity in the air, that is 0.03437 kg per kg of dry air. It is coming, it is being heated through an air filter. The temperature increases to 190 degrees Celsius and it is fed to the combustion. Fuel is coming 400 liter per hour. Stock is going heated up to 1340 degrees Celsius. Flue gas parameter is O2 is 12%, CO2 is 6.5%, CO is 50 ppm. This is the chimney. Now we know this formula. This formula we have discussed in boiler. So you have to remember this formula. So what is this? If any fuel analysis has been given, then we can calculate the theoretical air required for the combustion in the fuel. It might be coal, it might be oil, it might be gas. So what is the formula? 11.6 into C, 34.8 into H2 minus O2 by 8, 4.35 into S. That is the kg of fuel. So if I apply this, C is basically the percentage, O2 is 0.7, H2 is 12. So this is basically from the fuel analysis report. So from this, I calculated the theoretical air required for combustion. Now, what is the excess air formula? That is O2 by 21 minus O2. Same formula as like boiler. So excess air is being supplied at 133.3%. Is a good amount of excess air is being supplied. So what is the actual mass of air supplied? This is excess air. So this is the theoretical air requirement. So what is the excess air or actual mass of air supplied for 1 kg of fuel? That means 1 plus TA by 100, that is 14.12. So since this is the air required, but you are supplying 133% higher, so total will be this into 1 plus this percentage. So that means actual mass of air supplied per kg of fuel is, that is known as AAS. Remember, AAS is 32.94. So AAS is 32.94. Now this will be required to calculate lot of data. Now, what is the mass of dry flue gas? This also you have studied in case of boiler. Same formula. There is no change in formula. So mass of CO2 is basically, you have to understand what is CO2, 44. There is a molecular weight. N2 each, particularly sulfur dioxide each. This is particularly the sulfur dioxide. Sulfur dioxide is 64. What is mass of N2? Oh, in the fuel, it is 0.5%. That is given in the proximate analysis or the fuel analysis report. Now, what is mass of N2? That the 77 is the weight of the N2. Oxygen weight is 23. So if you have to remember this formula. Formula is 85859. It becomes mass of CO2 into 44. Why? This one basically is coming from this. Carbon is 85.9. From this, you got C is equal to 85.9. This is in percentage. This is an N2. So from this, we can calculate mass of dry flue gas is 32.86 kg per kg of coal. This is one method to calculate mass of dry flue gas. Another method is this one. What is this method? What is the amount of wet flue gas? AS, that is actual air supplied, plus 1, that is 33.94 kg of flue gas, because this is the one is the kg of fuel. Now you know this formula, amount of water vapor, that is MW. Remember this formula, amount of water vapor in flue gas is M plus NH2. What is M? M is the moisture in fuel, S means hydrogen in fuel. So because the fuel, there is certain amount of moisture and hydrogen there, so when it is burnt, you get water vapor. So what is the amount of water vapor we'll get? M plus 9H2. That becomes 1.084 kg of H2O per kg of fuel. So 1.084 kg of H2O is being released because of burning of this 1 kg of fuel. So what is the actual amount of wet gas was? 33.94. So what is the amount of dry flue gas then? So 33.94 minus the water vapor. So if I calculate what the amount of dry flue gas, I'll find out also 32.86, which is similar to the other one. So these are two methods. Now, what is the specific fuel consumption? What is the formula? Amount of fuel consumed divided by amount of billet. Now, ton per hour. So you can convert it to also kg. That will be also correct. So 368 is the fuel consumed divided by 6. That is the ton per billet. So it is 61.33 kg of fuel per ton of billet. So this is one formula we have already calculated. That's specific fuel consumption. Now we have to calculate what is the heat input. So how to calculate the heat input? Amount of fuel consumed per ton. What is the amount of fuel you are providing? So amount of fuel or input fuel is basically fuel consumed into GCV. So from this GCV is 10,000. Fuel consumed is 61.3. Now what is the sensible heat of fuel? Now this is important. Q2 is basically when it is reaching to a burner, the temperature of the fuel also increases. Now this 100 degrees Celsius is basically the burner temperature or the side wall temperature. If you see this one, the temperature has increased to, let us say, side wall is 100 degrees Celsius. So you are also assuming that temperature of the sensible oil also has increased to 100 degrees Celsius. So this is the final temperature. But ambient temperature is 40 degrees Celsius. So the you are also supplying some amount of, because you are providing heated oil. So some amount of heating of the oil has occurred, due to which some amount of sensible heat has been taken inside the furnace. So what is that? F is the fuel consumed, Cp is the specific heat, which is 0.5, delta T. Delta T will be 100 minus 40. So 1840 kilocalorie per ton of billet is being consumed, or the heat taken inside, as well as sensible heat. So what is the total heat input? One is the latent heat, or the combustion heat of the fuel. Particularly, this is the combustion heat of the coil. If I burn it, I'll get it. But this sensible heat is due to the temperature heat of the coil. So these are the two heats. That is the heat, total heat input is 615140. Now let us calculate what are the heat output. So one heat output will be heat taken away or carried away by 1 ton of billet. So 1 ton of billet means this is the mass. We are calculating everything in 1 ton. So that we can conduct the heat balance accordingly. So Cp is specific heat, that is 0.12. 1 ton means 1000 kg. Delta T 1340 is the outlet temperature, 40 is the ambient temperature. From that we got Q3. Now what is the heat loss in dry flue gas per ton of billet? We have also studied, that is the fuel consumed, amount of fuel consumed per ton of oil into mass of dry flue gas. So mass of dry flue gas into Cp. Cp is here in this case is basically 0.26. How it is 0.26, that we will be studying in next class. It is written in also given in para 2.9 of the book. So mean specific heat of the flue gas is 0.26. Also you can remember, there is a table from which you can find out. Since this is an open book, you can find out this figure 0.26. So Cp is the specific heat. T1 is temperature of the flue gas is 655. It is given data. Ambient is 40. So delta T we can find out. So F is 1.33. That is the amount of fuel consumed per ton of billet. That is the specific fuel consumption, into M is 32.86. That has been already found out in terms of here. 32 dry flue gas is 32.86. So from this we can find out the heat loss in dry flue gas per ton of billet. That is Q4. Now what is the heat loss due to formation of water vapor from the fuel per ton of billet? This is Q5. Q5 is basically, since some amount of water is there in the, particularly in the billet or in the fuel, therefore some amount of heat will be lost due to the formation of water. So let us find out how to calculate that heat loss due to formation of water. Now F is, we have 61.33. M already we have calculated 1.084. That is the mass of the M plus 9H2. From that formula, we have already calculated 1.084 in the previous one. This M, particularly if you see, this is the M, 1.084. That is the amount of water vapor in the flue gas which has been released due to content of moisture and hydrogen in the fuel. So M we know 580 for, this is the formula, 580 for Cp into delta T. Delta T is basically 655 minus 40. And what is this? Cp of superheated vapor. Now because this temperature is very high, this will be superheated vapor. So specific heat of superheated vapor is 0.47. Now heat loss due to moisture in the combustion air. Some air also contains some moisture. What is the moisture? That is the humidity of air. Now what is the humidity of air? It is the formula, or it is the data given 0.03437. What is actual mass of air supplied? Actual air supplied is 32.94. Already you know. F is 61.33. Cp is superheated vapor. So specific is 0.47. From this we calculate the heat loss due to moisture in combustion air. Now heat loss, so, all the carbon is not converted to CO2. Some amount of CO is also released. So there is a heat loss. We know heat loss due to partial conversion of C to CO. This is also you have studied in boiler. That is F into percentage CO into C divided by percent CO plus percentage CO2. So what is this formula? This is 5654. That is the actual heat loss due to partial conversion of C to CO. So 5654 is the one type of heat loss. So from this we can calculate Q7 is 229 kilocalorie ton of billet. Now after that we need to calculate Q8. What is Q8? Amount of heat loss from the furnace body and other section. That means some radiation losses are happening. So let us find out what is this Q8. Q8 is Q1 plus Q2 plus Q3 plus Q4. Now what are the Q1 to Q4? Let us understand. Small Q1 to small Q4. Q1, small Q1 is heat loss from the ceiling. Q2 is heat loss due to sidewall. Q3 is heat loss due to bottom. Q4 is the heat loss due to flue gas duct. Because there is a air preheater, so there is a flue gas duct. So some amount of flue gas duct also up to till the duct or till the air preheater, some amount of heat will be also lost. So let us calculate what is this Q4. Now you have to remember this formula. For particularly to calculate this type of radiation losses, we need to understand this formula. This formula tells that H, any heat loss will be H delta T to the power 1.25. A is basically some kind of area. Then the formula 4.88 into emissivity. Emissivity data will be given. This area will be given. H you can know from the table or in the book it is given. Tw is the temperature in Kelvin or the external temperature that is in Kelvin. This Ta is basically the ambient temperature. A is again area. Now by applying this formula, let us see what is H. This is natural convection heat transfer rate. It is 2.8. It is given data in the book. It is table is there. The furnace, the temperature outside, if I convert it to, it will be 358. Why 358? Let us see. The temperature it is given here. Temperature is side wall, ceiling is 85, surface wall, side wall is 100, flue duct is 64. So you have to remember this three temperature so that you can convert it to Kelvin by adding 270 plus 273 plus 273 plus 273. Now T stands for Kelvin. Now if I, so it becomes 85, 85 minus 40, it becomes 45. Surface area of the ceiling is 15, given data. Emissivity is given data 0.75. So from that we can calculate Q1. It is 8644 kilocalorie per hour. Similarly, Q2, H delta T 48.88 emissivity, this formula. But in this case, for particularly for what is this one? Q2 is sidewall H is 2.2 and external surface is 0.75. Sidewall area is given 36. Now delta T is 60. Why? The sidewall temperature is 100. 100 minus 40 is 60. But you need to convert it to Kelvin because there is a formula here. So Q2 by applying you can calculate Q2. Q2 sidewall, you see sidewall losses is more as compared to the top one. Now bottom surface is not exposed to the atmosphere, so Q through has been ignored. So these are assumption. Otherwise, you can also calculate Q3 based on applying this formula. Now, what is Q4? Q4 is basically in this case there is a change in formula. In this case, some D has come. What is this D? D is basically outside diameter of the flue gas duct in meter. That is 0.4 meter. So H delta T 1.25 divided by D. So because there is a from the furnace to the air filter there is a duct, so there will be some losses will be happening there. So for this we are calculating. Otherwise, all the other formula are same. Now what is that one? That one is 64. That is the duct temperature. So 64 minus 40 is becomes 24, and we have converted to these two TWTA into Kelvin. By applying this formula we have calculated Q4 is equal to 2001 kilocalorie per hour. So Q8 will be small q1 plus q2 plus q3 plus q4 by amount of billet ton per hour. That is, these are all in kilocalorie per hour. So this is the amount of billet. So you have to divide it by 6. Remember, we have to divide by this 6 to get q2. That is kilocalorie per ton, because we are calculating everything in kilocalorie per ton. Now there is another formula, that is heat loss, radiation heat loss due to furnace opening. You have understood there is a 1 meter into 1 meter opening is there. Wall thickness is particularly 0.46 meter. So there will be some heat loss. What is the formula? That formula is amount of open time during the period of heat balancing. So HR into area, that is 1 meter into 1 meter, that is 1 meter square. It is a square opening. This coefficient based on the profile of the furnace opening. So there is a table. If you see in the books 2.9, there is open book table 1. You have formula, and this value of 0.7 is given. So based on this temperature and the thickness, we have to divide shortest side. Shortest side is in this case 1. Wall thickness is 0.46. So you are getting 2.17. So you have the value, this 5 value for 2, you have the 5 value for 4. By interpolating or by calculating, you can find out what is this 5, that is 0.7. Just go through this 2.91 table, it is mentioned there. Now what is TF? TF is 1340 degree Kelvin. So from that we can calculate plus 273. And what is the T0? It is 240 plus 273, that is 613. So from this I can calculate, this is 1 is the let us say opening time is 1 hour, and this A is area is 1 meter square, 0.7 is the 5 value, 4.88 then ambient by 6. 6 is the ton. So Q9 is the furnace loss due to opening, or the heat loss due to opening, 38485 kilocalorie per ton. Now, there must be some other type of losses which cannot be counted. These are known as unaccounted losses. So, what are those losses? Heat carried by cooling water, heat carried by bottom of the furnace, heat accumulated by the refractories, some instrumental errors, others. So, these are the unaccounted loss. So, what is this unaccounted loss? Total input loss minus the total output loss so far measured. So, Q1 plus Q2 minus Q3 to Q9. So, these Q3 to Q9 already we have calculated. From that we know Q10 becomes 131945 kilocalorie per ton. So what is the total output? If I add Q1, Q3 to Q10, I'll get total output. So you see Q1, this Q1 plus Q2 now is equal to total output. So heat input is equal to total heat output. That is known as heat balance. Heat input, that is Q1 plus Q2. What is heat output? Q3 to Q10. So both the things are now matching. So both the heat input and heat output are balanced. Now what is the efficiency in this case? Heat carried out. This is the useful heat. This one is the useful heat. So heat carried out by billet by combustion heat of the fuel. So it is the heat input. So 25.4% is the furnace efficiency. So where during audit period, what exactly we do? We really attack the maximum losses. Now see what are the maximum losses in this case? Is the dry flue gas losses. So furnace control, the air excess air control, the furnace heat recovery are the major parameter as far as furnace efficiency or energy conservation is concerned. So normally Q4 is the major area where you need to focus. Other area is very negligible loss. Only furnace opening is a major loss we need to control. So with this I conclude this furnace efficiency or assessment problem, you just go through the books. It is also mentioned there, but you need to practice this the calculation, and only it will be easier to do or calculate during the examinations without any delay time. So in the next class we will study something more on the chapter book 4 of furnace, and we'll then after that we shall conclude the sessions. Thank you and good night.